Okay, so this is me again, Zulfan. So we are talking about we have learned linear programming. We have learned non-linear objective functions, but linear constraint. Now we talk about integer and mixed integer programming. We'll discuss about how to formulate an integer programming problem. We'll talk about branch and bound method, depth and breadth of the method, and then we'll see what mixed integer linear programming is and what mixed integer non-linear programming is all about. Integer, as we recall last time, that it talks about instead of continuous variables, we have now integer variables about how many reactors, for example, and is it 1, 2, or 3, or 4, and so on. And then what is the type of reactor? Is it PFR, plug flow reactor, CSTR, or it's a batch reactor, or is it like a heterogeneous catalyst? Is it like a distillation? How many of them, and what type of materials? These are all integer variables. We can say that it's 1.5 distillation column, for example. Some of these integer can also be like 0 or 1 value, which is then binary integers, such as are we going to install new piece of equipment or not? Are we going to mix the streams or not? If we say yes, that means it's 1. If it's not, then it means it's 0. We typically refer to continuous variables as x variables and an integer variable as y variables. If we combine them, that means we have a problem called mixed integer. So yeah, still the objective formulation is about minimizing an objective functions with this inequality constraints of having continuous and an integer variable, as well as the equality constraints having either or both the continuous and binary or integer variables. If all of them are linear, that means we have mixed integer linear programming. If any of these objective function constraints, either it is equality or inequality constraints, is non-linear, that means we have a mixed integer non-linear programming at our hand. So now, for example, if we have reaction A to B, yeah, and then if we have reactor 1, so the conversions of reactor 1, we have the different catalysts in reactor 1 than in reactor 2. So we have 80% of conversion A, with the cost of the operation is then 5.5 feed times feed to the power of 0.6. Yeah. And then the conversions of reactor 2 is slightly lower, so 66%. It's also a cheaper cost of processing, 4 times feed to the power of 0.6. And then x0 is the feed flow rate, so we have to pay the feed as 5 pounds per kilomole, and we have the desired product B of 10 kilomole per hour. So we have two combinations of reactors, reactor 1 and reactor 2, independently. So we have two parallels independent. We have some of the reactant A goes to reactor 1, and some of the reactant A goes to reactor 2. So we have also like a parallel, but they are simultaneously used to get product B. So we have two options, either a standalone reactor or two parallel reactors. So the objective function is then to calculate what the capital minimize the cost. So because we have the cost of reactors, operating cost, and we have the cost of the feed. So now we have a capital cost of x1, of reactor 1 plus reactor 2, and then the material cost of the x0. And then we have the constraint mass balance at the initial split, which is this x0 equals to x1 plus x2. And we have also a mass balance over here, z1 plus z2 equals to 10, and z1 equals to 0.8 x1, yeah, 0.8 z1 is 0.8 x1, z2 is then 66.7 or 0.66 times x2. So now we have how many variables? X0, X1, X2, Z1, Z2. So we have 5 variables, we have 4 equations. So it's 1 independent variables which we can optimize. So if we eliminate 3 dependent variables Z1, Z2 and X0 from the constraint, to simplify it, so it means we have this objective function as the constraint, objective function as a function of x1 and x2, and we have this x1 0.8 x1 plus 0.667 x2 equals to 10 as the constraint. So if we eliminate x1, so we do direct substitution. So x1 equals to 10 minus 0.667 x2 divided by 0.8. So we will plot then C as a function of x2. So we can see that if x2 equals to 0, we can calculate how much x1 is, and then it's only using reactor 1. So we have this 87.5 as the objective function, and then if we have 15 only reactor 2, which means x2 equals to 15, x1 equals to 0, we have 95.3 as the objective functions. And somewhere in between, for example, if we have 11.4, we get 99.8 as the maximum points. So in this case, if we see this graph, we have 2 minimum points. So either here we use fully reactor 1 or reactor 2. So if we start our search from here, for example, so our algorithm will tend to go in these directions. Because we are going to search for a minimum value, not in these directions. Not because if we go this way, we are moving upward. So it will then automatically tell us that we have to move to the right, which is going to we are going to go lower and lower in the objective functions. So in this case, if we start here, we'll stuck, or we will arrive at this point, 95.3. But if we somehow use a different starting point, will end up in this directions with this at this point. So so we can see, depending on the initial point, we can end up at 2 different how do you call it, solutions. This is then the results if we formulate this problem with only continuous variables. But let's see if we try to introduce an integer variable to this equation. So let's see, we have like two other variables, y1 and y2. y1 is equals to 0 if reactor 1 is y1 equals to 1 if reactor 1 is selected, y1 equals to 0 if reactor 1 is not used, and then y2 equals to 1 if reactor 2 is used, and then if it's not used, y2 equals to 0. We try to incorporate these 2 variables with these equations. So x1 minus m1 y1 less than or equals to 0. m1 in this case is the upper limit, m1 and m2 is the upper limit, for variable 1, variable x1 and variable 2 respectively. So it can be any big number, has to be big enough so that if say y1 equals to 1, that means 1 times something very big, when we use that x1 minus something that is very big, it has to be negative. So the highest number of x1 that is applicable has to be negative when it is when we minus it with f1, m1, y1. If we use 1, y1 equals to 1, that means we have a value of x1, but it will be negative. But if we use if y1 equals to 0, that means x1 has to be 0, because if this is 0, y1 equals to 0, m1 times 0 is 0. So x1, in order to fulfill the constraint, it has to be 0 as well. So you can see it now here. The same goes with the y2. So how to calculate the upper limits? Upper limit of x1 in this case, because it's easy. So we know that B is required to be like 10 kilomole per hour. And then this 10 kilomole per hour, if we use x1 only, that means 10 divided by 0.8, it is then 12.5 kilomole per hour. The same goes with x2. M2 is then 15 in this case. For this simple case, yes, we can calculate that, but for more complicated case, we can just use big numbers, big enough to make sure that it has to be negative. Now we try to formulate that. So we have these equations, same objective functions, but now we have one continuous constraint, and we have now additional two equality constraints with the binary variables. So now if we just play around with y1 and y2, if y1 y2 equals to 0, 0, we have invisible solutions because we are violating the mass balance. This has to be equals to 10. So if y1 y2 equals to 0, that means x1 x2 has to be 0, which is not possible. And then if we use y1 1 and y2 equals to 0, we get 87.5. y1 0, y2 1, we have 95.3. And then we have y1 is 1, y2 is 1. In this case, so x1 and x2, well, I have to, if it's 1 and 1, x1 and x2 will be somewhere, will be yeah, some values that should also satisfy this constraint. So in this case, we might end up having 99.8. So we can see now, if we want to minimize the whole this problem, y1 has to be equals to 1 and y2 has to be equals to 0, which means x2 equals to 0, and then x1 is then the maximum value, which is then 12.5. So now branch and bounds. Branch and bound, we solve problem as if it contains only continuous variables. And if the optimal solution contains non-integer values for some integer variables, so it has to be like integer variables, but the result, so if we treat them as a continuous variables, the result shows that it is a continuous solution. It is, I mean, it is not, it is a non-integer value. So we have to then partition these variables, these integer variables, into subsets. We'll see that later on in a minute. So, and then number 3 is then if we now do the branching, so we apply also to some bounding methods to stop our branching the solution. So now let's use a simple example. Z, we want to maximize Z equals to 3x1 plus 2x2. The constraint is then x1 less than equals to 2, x2 less than equals to 2, x1 plus x2 less than or equals to 3.5. x1 and x2 in this case are integer variables. So number 1, we solve the problem as an LP problem by ignoring the integer restriction. So now we don't see this as an integer variable. We see this x1, x2 as a continuous variable. So now if we use this in Excel, so if we now do find x1 and x2, and then x1 plus x2 has to be equals to or less than 3.5. So I put this x1 plus x2, and then the z is then, so I put this function z of 3x1 plus 2x2. So if I run this to maximize z, I get 9, and then x1 is then 2, x2 is 1.5. Okay, so this is then the solution for our linear programming. But now we see x2 is okay, because x1 is okay, x1 is 2, and it fulfills the integer criteria, but x2, it is violating the integer. It is 1.5, it's not supposed to be the case. So now it is 1.5, we have to split it. We split it into larger than or equal to 2, or lower than or equal to 1. So we split it into 2. Yeah. Less than or equals to 1 and bigger than or equals to 2. So we have now 2 additional linear programming problems, and then the same, you can see now it's the same solution, same problem, but then we have this additional constraint, x2 equals to or less than 1. and then we have also this as another constraint over here. So now we have two linear programming problem which we can easily solve. Now we see now the second linear programming problem, x2 equals 2 or less than 1. So we see that x1 is 2, x2 is 1, and then the x2 plus x1 is 3, which is then less than 3.5. So z is then 8, and the LP3 x2 we get x2 equals to 2, but then x1 is now violating the integer. So we have to split x1 into 1 and then into 2. So if it's into 1, so we get z equals to 7. If we make it x1 into 2, we violate the constraint for x2. So if we put them all in the in this branch and bound figure, so we have the first one is then the first linear programming problem, node 1. We have z equals to 9, but x2 is not feasible, so we split x2 into 1 and 2. So we have LP2, so we have z equals to 8 in this case, and the other one is then x1 is not feasible, we split it again. So this is a feasible solution, this is still not feasible solutions if x1 equals to or bigger than 2. So if we now trying to maximize the z, that means we have two options only. X1 is 1, x2 is 2, z equals to 7, or x1 is 2, x2 is 1, z equals to 8. So in this case, this is then the optimal solution. So this is basically the branch and bound method in its simplest form. But what if there are more than one integer variables with fractional values in the solution? Which one should be selected first for branching? So in this case, we are lucky that we have only like one variable which needs to be branched. But what happens if both x1 and x2 are not integers in this case? Yeah? So the guidelines is then we have to select integer variables with the largest fractional value. So if we see the z functions, so z is 3x1, 2x2. So the largest is then x1. So if both x1 and x2 are found to be non-integer in the solution, so we have to then split first x1. Number 2 is then assign parameters to those variables and select the most important one, either based on the like its important decision in the model, which you know it, or its cost or profit coefficients in the objective function is the largest, like we know it in the first guideline, or the value is critical based on users' experience. Or number 3 is just like arbitrary selections. There is no significant difference. We see the branch, but now how about the bound? Now the bounding method is then if we assume that z star, the objective functions calculated by is the optimal solutions to the relaxed linear program at node I, yeah. So at node I we calculated already the objective functions I. If the node I is a parent node to node J, that means we're going to split this into J. Then Zi here has to be less than or equals to Zj, because now we are now trying to minimize it, yeah, by definition. And number 2 is then if this is not feasible, that means all of these descendants are all infeasible. That's true, yeah. So this has to be lower than this and that. That's number 1. Number 2 is then if this is not feasible, we don't have to waste our time to find the child or the branch out of this node I, because if I is not feasible, then its branch J are all infeasible. Another example is then if we evaluate 3 of solutions, yeah, instead of this branch and bound method to find some optimization, these 3 of solutions we can also evaluate it in a different way. So we do depth first, we do breadth first. So that means breadth means we split it first, as many as possible, but depth means we are now trying to split it once and then split again and then split again and then split again. So we complete the whole search in one branch, and we do another branching at the other point. The general problem of mixed integer linear programming is, I think we have seen this over and over again, and then we know now that MILP problems can be solved by using branch and bound technique. So if we have another example like this, and then we try to solve it like what we've done so far. So this case point x1 or y1 and y1, y2 and y3. So y1 is 0.2, y2 is 1, and then the y3 is 0. So y1 we have to split either 0 or 1 in this case. So split it to 0 over here, 1 is over there. So this one we maximize it again, and then we see that the y2 is now half. So now we split y2 into 0 and then 1, so we get this, and then here we get that one, and we split y3 0 to 1, and we get this one. Y2 is becoming invisible again, so now we split y2 0 and 1, so we have this. So we have z equals to 8 with this y1, y2, y3, z equals to 9 with this y1, y2, y3. Yeah, so if we want to minimize it, that means we'll select this. The branch and bound tree uses a breadth first enumeration, so it will then use the breadth first. And each node, some binary variables are fixed with others treated as continuous variables. This results in relaxed LP problem. We've seen this. And if node I is a parent node to node J, as we have discussed, so Zi has to be less than or equals to Zj because we want to minimize it. And then if node I is invisible, then all of the descendants of node I, they are all invisible. Some comments on the modeling aspects, because these binary variables are very useful. Some examples. So you have like a multiple choice constraint. For example, we have to select only one item out of the whole integer variables. So it means the summations of all integer variables yi summation of yi has to be equals to 1. If we have to select one item, so it means the summation has to be less than or equals to 1. If we have to select at least one item, the summation has to be greater than or equals to 1. If we have some implication constraint, if item k is selected, then item j must be selected. So we do it this way. So if we see that if yk equals to 0, right, that means item k is selected, this yj has to be 1. So if yk equals to 1, because k is selected, that means yj has to be equals to 1 to fulfill this constraint to become 0 or less than equals to 0. If it's 0, that means it can be 1 or 0. Either one is fine. If a binary variable y is 0, an associated continuous variable x must also be 0. In this case, we have seen this. So if y1 is then 1, that means x has to be a number. But then if y equals to 0, that means x has to be 0 as well. And then we have also either or constraints of disjunctive constraints. So either constraint J1 or constraint J2 is used. So it means we can have so if y equals to 1, that means if J1 is going to be used, that means y1 equals to 1. If J1 is not going to be used, that means y becomes 0. And then the corresponding constraint is then J2 minus u times 1 minus y. So I think you can see this in Bigler's book. Yeah, I just put an excerpt from this book, which is very important and very useful. Example on the constraint, if we have like a absorber or membrane separator, if either of them is selected, we are not going to use cryogenic separation. So how to do this is that YA is absorber, YM is membrane, YC is cryogenic. If either of these absorber or membrane is used, cryogenic is not going to be used. So that means YA plus YC less than or equals to 1. So if we see now here, if A is then used, that means YC has to be 0 because it cannot be 2. The same goes YM. If YM is 1, that means YC has to be 0. But if YM is 0, YC can be 1 or 0 depending on how much is YA. But if both YA and YM is 0, that means YC can be 1. How about mixed integer nonlinear programming? Mixed integer nonlinear programming is the hardest to solve. Yeah, I intentionally skipped the nonlinear programming until the last chapter just to give you an idea on how we are going to incorporate the nonlinear programming without without getting into details yet on how to solve it, because it will take most of the time and it's also very difficult to do manually. So this is then a specific form of mixed integer nonlinear programming. So we have the objective functions consisting of integer or binary variables with continuous variables, and then we have nonlinear equalities of continuous variables, nonlinear inequalities with continuous, linear equalities of mixed variables, and inequalities of binary variables. So these are then typically the form of MINLP. Principally, we can solve this by using the branch and bound method, as we see in this lecture, that we solve the linear programming, the mixed integer linear programming, with the branch and bound method, where in each node we use linear programming to solve it. But now in mixed integer nonlinear programming, we have to use nonlinear programming to solve each node. Yeah. The important drawback of this branch and bound method for MINLP is that there will be too many NLP subproblems, which we know it. So in order to reduce the computational time, there is some approach, generalized band decomposition. So you are advised to go to this reference or outer approximation method. We will see that in the other slide. Yeah. So basically, this is the case. So we have the initial guess. So we solve the submodel mixed integer linear programming, master model nonlinear programming, and if we have the tolerance of these two, is then the difference between them is less than the tolerance. If not, then you go back, change the new x. If yes, then you stop the optimization. So these are then some common available software and resources that you can look further after finishing this course. So Microsoft Excel has a simplex linear programming, GRG method, and evolutionary methods, for the genetic algorithm. So we have we also like a general algebraic modeling system, GAMS. Yeah, we could also have like Lingo, and we have MATLAB. We have Epimonitor online optimization. So we have Python also optimization. So we have there's other two other resources which you can also look at to solve optimization problem. I think with this I conclude my presentation.